Hi, Calculus. It's Mrs. Jarosik here. I am actually doing a retake on 4.2, the first part, because I had some serious technical issues, which ended up just being very uncooperative. So, long story short, I changed my scenery a little bit, took a little walk. I was a little bit frustrated. And we're back again, and I'm going to reshoot this video, at least the first part. The technical difficulties started at the end of where I was getting to, and I redid a video specifically for one portion of this. So I'm only reshooting one piece. I guess you don't need to know all of this, but that's the way the day has gone. Okay, so I'm going to start over and talk to you about 4.2, and this is the first video of 4.2. There will be actually 3 in the end. There'll be this one, the one when the first technical difficulty happened, rounding out this same notes packet, and then there is a second one for a different notes packet. So it's okay because the material in 4.2 is pretty meaty in content, and there is a lot to it, and it carries us through the entire chapter 4. So I'm going to just get started. And 4.2 is, if you don't have your notes printed out already, also pause and you want to go ahead and do that or get your notebooks ready. Okay, so chapter 4 is titled 4.2, is what derivatives tell us. And we are going to specifically talk about intervals of increasing and decreasing and relative maximas and minimas, as well as the first derivative test. So we're going to be able to locate intervals of increase, decrease. We're going to locate relative maxes and mins, and we're going to learn how to use the first derivative test in this section. Okay. All right. I am actually skipping over the opener. I skipped over it last time as well. It's a great opener, except with the time I know that's going to be taken for going over the material in this section, this will be very time consuming and add to the length of the video. If your teacher does have time in class, it might be a great problem to go over in class. If not, try it on your own, and then the key would be posted. Okay. All right. So I'm going to scroll down here to the first graphic that I have in the notes. And it is actually out of the book, and it has several things that we talked about in section 4.1 already kind of labeled, right? And I already took a few notes prior. Feel free to just pause and you can jot these down, but these are sort of refreshers from 4.1. And our refreshers being, we talked about absolute maximums. They're the largest y values, and our absolute max on this problem is this. And what's required for an absolute max? Actually, hold on that thought. Absolute mins, then I will talk about this, is right there and labeled smallest y value, critical point. We talked about critical points. It's the x value where the derivative is equal to either 0 or it is undefined. And we have all of those labeled here as well. F prime equal to 0, f prime equal to, there it is, 0 for that, and f prime equal to 0. And then right here, where the absolute max was, that was actually where f prime is undefined. We talked about the extreme value theorem, EVT. To hold or to be applicable, EVT must have 2 conditions. There must be a continuous interval, and that interval has to be closed, okay? And if you have that, then you're guaranteed an absolute maximum and an absolute minimum. So I was kind of getting into that a little bit too early with what I had written down. What I was going to say is, how do I know I will have an absolute max or an absolute min? Or I should say and instead of or. It's because I had a closed interval to begin with, right? And my function is continuous, that is drawn. We learned about the candidate's test for absolute extremes. We take our critical points, we take our endpoints of the closed interval, and we test them all in the original function to find our absolutes. We have local or relative maxes and mins. A local or relative max is the largest y value in that area of the graph or of the function. And the local relative min is the smallest y value in the area, in that location of the interval you are looking at, okay? All right, just some refreshers. And We have some other things noted on this picture as well. So notice where it says we have f prime is greater than 0. Have any other greater than zeros? I think that was it. And when it's greater than 0, oh, I missed one. Sorry, right there, right there. Where it's greater than 0, notice what f is doing. It is increasing. It is increasing. And when f prime is less than 0, what are we doing? We are decreasing. So those places, right there, we have decrease on f. So that goes hand in hand with the chart in this portion specifically. So if f is increasing, we have a positive derivative. F is decreasing, we have a negative derivative. Okay, all right. All right, the chart you will see is going to be recreated several times over while going through these. All right, let's start out with our intervals of increasing and decreasing. So to find critical points, first step is to find critical points. Set up your intervals using the critical points and the domain of the original function. And then use a test point in each interval using the derivative in its factored form to determine if the derivative is positive or negative. All right. So with our first example, we are going to take the derivative of f of x equals x times e to the negative x. This requires product rule. Okay. So f prime of x is e to the negative x plus x times negative e to the negative x. And it's not that I ignored taking the derivative of x, it's just 1. So again, we could have that in front when we do this. So if I simplify this a little bit, this would look like this. And to find critical points, right, they're where f prime equals 0 or is undefined. Okay. So e to the x functions, whether they're e to the positive or negative x, are never undefined. Okay. So we are literally just finding where it's equal to 0. So I'm going to do a lot of factoring in this section, and I'm going to go ahead and factor right now while I set it equal to 0. I can factor out an e to the negative x. I'm left with 1 minus x. Okay. So 0 product property says e to the negative x gets set equal to 0 and 1 minus x gets set equal to 0. So I definitely have my derivative being equal to 0 at 1, critical point at 1, and then e to the negative x equals 0. Well, e to the negative x, e to the x, can never be equal to 0. So remember what e to the negative x is. It's actually that one, right? Still doesn't cross or touch 0 or go below it. So there is no x value that I can actually plug in there. So this doesn't result in a solution. All right, one and only critical point is x equals 1. I'm going to make a little number line with my critical point. I'm going to test on the left side of 1. I'm going to test on the right side of 1. You can pick a number less than 1 that is super close to it. You could pick 0. I love picking 0. It's a great number to pick when you can. You can also pick negative 5 million if you want. Numbers greater than 1, you could pick 2 or you could pick 500. It doesn't matter. So when I pick 1 and I go back to factored form, you want to go back to your factored form to test this out, okay? It's the easiest place to go back to. So if I pick negative 100, let's say, well, e to anything, e to negative x when x is anything, e to the positive x when x is anything, guess what? It's always positive. We just talked about that. But 1 minus either 0 or some negative number is going to result in a positive value. So to the left of 1, we are positive. Okay. And then on the right side of 1. So if I put in anything large like 100 or 2, doesn't matter. 1 minus 2 is negative, 1 minus 100 is negative. E again to anything at this point is positive, so we have a positive times a negative, which gives us negative overall. So if we're finding functions, intervals, excuse me, of increase and decrease, we are ready to write our answers. Remember that when our derivative is positive, we are increasing. When our derivative is negative, we are decreasing. Now we just need to make statements saying that. So f is increasing on negative infinity to 1 because f prime is positive. And f is decreasing on 1 to infinity because f prime is negative. Okay. All right. Second example, polynomial. Okay, we like polynomials. Polynomials are very nice functions to work with. Okay. So critical points come first. I'm going to take G prime. As always, before I start this, if you think you understand the concept of this, I would say pause and try it yourself. All right, 6x squared plus 6x is my derivative. And again, there are no places where the derivative would be undefined. It's a polynomial. So I'm just setting it equal to 0. And I'm going to factor. And I'm going to solve zero product property. Resulting in 0 and -1 as my critical points. So I put my critical points on a number line, and I'm going to start my testing of intervals. I need to test less than -1. I need to test between -1 and 0, and I need to test greater than 0. All right, let's start with less than -1. Let's put in -500. Let's think about this. A large negative number would be a negative times a negative, which is positive. And if I plug in something between -1 and 0, like -0.5, like just as my mental note, if that's what I'm thinking about. I have to be a little bit more detailed because that interval is much smaller. So if I'm thinking -0.5, that's negative. Oh, that's not my pen, negative. And then -0.5 plus 1 is positive, which means I am now negative overall. And then when I'm larger than 0, so whether it's 1, whether it's 500, whether it's 5 million, when I plug in, this would be positive. And then when I plug in anything larger, I would still be positive. So positive overall. Now, one thing I want you to understand is that regardless of the example choices, it is possible, and it is very possible, that you could have intervals that don't change signs each time. You could definitely have something that ends up being negative, negative, where there's no sign change, which means you wouldn't have whatever would require a sign change. Let's put it that way. Or if it was all positive, positive, right? It's just strictly increasing without any negative, right? If it was negative, negative, it's just all decreasing there. Okay, so keep that in mind. You have to do the testing, okay? All right, so let's write up our answer. So we could say that G is increasing, and we can combine our increasing intervals, meaning is increasing on negative infinity to 1 on -1, and from 0 to infinity, because G prime is positive. G is decreasing on -1 to 0 because G prime is less than 0. Okay. This will be the last one before the computer glitch happened. So this will be the last one. And then you're going to start right up with the next video, which will conclude the notes, okay, for this part. All right. So our next one, h of x equals x squared ln x. Well, in this set of notes here, so domain of original function, there's nothing noted here for us, but remember, definitely have a domain restriction on ln x. X has to be larger than 0. You can't take the log of 0 and you can't take the log of anything negative. So that already has its own domain restriction. Okay, so let's go ahead. Product rule is required. Take the derivative. 2x ln x, and just for purposes of, right, rough sketch of ln x. So that's, I took the derivative of the first part, left the second part alone, plus x squared times 1 over x, derivative of ln x. So simplified a little bit, and x squared divided by x is just x. So we are undefined for anything 0 or less than 0. So we already know that part, right? But there's a range of, or I should say, there's an interval of values that are not defined. It's not just a critical point, right? It's a whole area. So I'm going to factor out my x, 2 times ln x plus 1. And I will set this equal to 0, because I do need to find if there are any other places the derivative would be equal to 0. So this results in x equals 0. We already know we're not going to use that as a critical point. We can't even plug in 0. And we are going to set 2 ln x equal to, I jumped the gun a little bit. I was going to subtract 1. Plus 1 equals 0, which means 2 ln x equals negative a half. And I'm jumping the gun. Sorry about that, everybody. It's been that kind of a day with the videos. Ln x equals negative 1/2. All right, what does that mean? Well, let's exponentiate both sides. E to the ln x, e to the negative 1/2 would result in x equals e to the negative 1/2, or what is it? 1 over square root of e. All right, so this one's going to require a tiny bit more analysis. It's still a non-calculator situation. So what I am doing, if I have 0 here, right, we're limited. We have nothing there, and we don't even use 0. But 1 over root e, obviously larger than 0. And as far as a number between 0 or 1 over root e, or a number larger than 1 over root e, I guess a number larger than 1 over root e is a lot easier to analyze. I would say go for 100, go for 1,000,000, go for that idea, and it's probably pretty easy to analyze. So if I go back to factored form, which is right here, and I think about plugging in, like, 100 positive, and if I plug in 100 here, still positive, right? So positive times positive, we're positive. We're larger than 1 over root e. Between 0 and 1 over root e is still a positive value, but I would say just pick something super close to 0. And when I say super close to 0, I'm thinking maybe 0.00001, lots of zeros and a 1, something super small. So we can actually reference back to the graph a little bit here to help us out. So if I'm plugging in something super small, well, that's still positive. Nothing is changing there. But if I'm plugging in something super small right here, if you're thinking about the natural log of something super duper small, right, really close to 0, well, if we're getting close to 0, look what it's doing. It's a negative value. It's a negative value, and it's getting larger and larger negative. So that means this will be much more negative than when you add 1, it becoming positive. You get what I'm saying? So that second portion will be a negative value. Overall negative. Okay. So now we can write our conclusion. Is it F? It's H this time. I went back to check the function name. H is decreasing on 0 to 1 over root E because H prime is less than 0 or negative, right? H is increasing on 1 over root E to infinity because H prime is greater than 0. All right. So the rest of the packet is within the next video. I apologize for the confusion on the videos, meaning you have to stop and start another one. But unfortunately, technology got the best of me today. So thank you for watching, and we'll pick it up where we left off on the next video. Okay.